So, welcome to this week's seminar. I say again, we plan on having typically at least one seminar a week. And I'm going to talk about reconstruction problems in rich tomography. But I'm not going to talk about all the rich tomography methods. I'm going to focus on a few illustrative ones. So first of all, what do I mean by rich tomography? Well, first of all, it's a very attractive term. I mean, we don't say tall tomography. I don't think we get as much funding really, but so it is a catchy word. But what we really mean is more than a scalar. So typically, for a lot of imaging inverts, you have a transmitter and a receiver. You have lots of transmit and receive locations, and typically you measure one scalar for each of those positions. And rich tomography is really where you measure more than just a scalar. So it could be a function of one or two variables, could be a matrix, could be something like a histogram, but in particular, spectra, diffraction patterns, and polarization states are quite typical ones. The diffraction pattern might be a 2D diffraction pattern. So you've got lots of possibilities. But I mean, the thing is, the measurement is now rich. It implies that we might want to find something that's also higher dimensional. So rather than just a scalar image, vector image, an image that's a function of something, function on the sphere perhaps, or characterizing a quite number of materials or anything. So here are some examples, not exactly all the examples that I do, but and these are taken from the application papers that are there. Small angle X-ray scattering is a very, it's actually becoming very popular in that you need an X-ray synchrotron source to do it. And there's quite a few of those around the world. There's national and international facilities. And then investing hugely in the kind of measurement apparatus they need to do this, without necessarily thinking how to do the mathematics. So you think hopefully somebody will do that. But it's very quickly going to be producing a lot of data from these synchrotrons. What you do is you get a narrow beam of X-rays. You can make it monochromatic, one energy, and then for each projection, you rest to scan the beam. So I like this sort of zero generation tomography that's given away. But for each of those beam positions, instead of just measuring what gets through, you measure a whole diffraction pattern. Right? That's why you need to rest to scan the beam. So diffraction pattern, so each other. So you have beam coming in, it hits the sample, and the sample is on typically a two-axis rotate and also translate stage. So for each projection, for each of the directions, it can scan into Cartesian direction. And then a camera that measures the diffraction pattern. Typically, you don't measure the straight through ray because it's way too bright. You can't blank that off. So it's called a dark field method because you're not measuring the bright spot. It's just the diffraction stuff. And what they want out of this is at each point they release each voxel. They think of a reciprocal space map, which is a function of the sphere basically. And that characterizes stuff. About it. Over here in Cambridge, they're doing something similar with electron diffraction tomography. So mathematically, that's quite similar to X-rays. Physically, it's like this on scale. And an idea, for example, is to get crystalline material like silicon, such as you make a chip out of. It would have a diffraction pattern with lots of spots, and with strain going through the path, the spots get blurry, and you kind of try and deduce the strain. Polarimetric neutron tomography Not so widely done. I mean, I think possibly it's only the neutron source in Japan currently that can do this. The neutron source is fairly common. You fire neutrons down a very long tube, and by the time they come out, they count as parallel beams. Okay? But also, when you make them, they come at lots of different speeds. And speed is kinetic energy, so also lots of energy. But a particular speed, so they have a race. You'll put a burst in and have a race, and the fastest ones get there first. So you clock the time for each pixel, and that tells you, so you kind of automatically get an energy resolved image without any expert trouble, because you just clock the time, and groups of time is a group of energies. Right? But also, neutrons have a spin. A little bit more about it. It's very much like polarized light, but the spin direction is in 3 dimensions, and it's changed by a magnetic field. So we'll come back to that one. And I've got time of light neutron tomography, but actually I'm going to talk about Bragg. I've said enough about neutrons already, but without the polarizing thing, you can do spectral tomography. A little bit of math. So the theory of ray transforms really belongs to Vladimir Sharapuzhov, who was a Rothschild fellow. Will be here later in the program. I'll keep name checking people who are going to come. And so let's just, to set notation, the X-ray transform is just the integral along the line. And so it's just a function. The line is x plus s times psi, and we integrate the s. So whenever s, we integrate it along the line through x and then the direction psi. So that's just the X-ray transform scalar. I mean, that looks a bit too much actually, because x is 3-dimensional vector, and so is a point on the sphere, and that's 5 dimensions. You only need 4 to specify a line, and the point is that typically you take x to be on a plane to say the starting point, and then you choose a direction. And that corresponds, for example, to the detector plane. So you can just choose a plane for x to be on, so that your possible measurement is 4-dimensional, right? Because for each direction, which is 2 dimensions, you have a plane of where that line goes through. Okay, so the transverse ray transform is a useful object in many problems. It's called the Sharapuzhov J. And we're defining it on the compact with functions that are close to the extent distributed distance scalar code. But what we do is we take a symmetric tensor field S for notation, symmetric tensor field on R3 Euclidean space, and now of course that's got 6 components, right? So what are we going to integrate? Well, we could just integrate each component just like it was 6 scalars, but there's a couple of natural things to do which depend on the direction, right? So one of the things we can do is to project perpendicular to the direction we're going. Right? So for each direction that the line's on, we just project perpendicular to that plane. Now that's a formula for doing it with a matrix, but obviously it can be done. And then for each ray, we get a metric matrix. So essentially we get 3 numbers for each ray, because it's really only a 2x2 matrix. Put it in the right plane, right? So it's 3 numbers per ray. But for rank 2, I mean, and it's defined similarly for higher rank symmetric tensor fields, and surprisingly, those are also useful. Okay, and then there's another one that's also seems very natural and turns up, called the longitudinal ray transform. it maybe seems more natural, because what you do is you get, say, this breakthrough tensor, figure metric matrix value function, and you project it in the direction that you're going rather than perpendicular to it, right? For other natural choice. So for a symmetric matrix or a breakthrough tensor, you just sort it either side with a direction. It gives you a scalar. Now think about that. For each line, 4 dimensions worth of lines, right? We now get only a scalar. So say this, what would happen if it was a scalar X-ray transform? So that does seem a little bit short of data, right? Because it's the same as a tensor. And indeed, that is the case. This one has a giant null space, which may or may not be the thing that you want. And in some cases where it seems to be almost the answer is exactly what you want, rather than the other bit. Okay, so that one's interesting in that way. There's a really simple way to invert J, the answer space, which I'd like to explain. It's in Shaw-Christoph's book, and it's just relatively simple, actually. You see, what you do is you think of it plane by plane. So, I mean, it's natural to do that in applications anyway, but think of just lines in one plane. And then we're integrating the perpendicular component of the matrix in a direction in that plane, right? Well, the component perpendicular to the plane doesn't really care which way we go. But the other two components will vary as you rotate the line around. You get different components of the matrix. So the one thing that's kind of easy is that component. So, you know, you've got a 2 by 2 matrix for each direction, but it's the component normal to the plane that you can get easily, right? And then the point is that that counts as a scalar from the point of view of the plane. Because it doesn't matter if you rotate, right? I mean, it's normal to the plane, so it's invariant of the rotation. So from the point of view of that plane, it's a scalar. And so integrating it is the scalar radical tensor of that component, which we all know and love. It's got an explicit inversion that's very commonly done. So we get the normal component of the tensor, and if it's a rank 3 tensor, we get the normal, and so on, right? Component, just from this procedure. And it may seem a bit wasteful because for each line we measured 3 numbers, and I'm going to go use 1. Right, we'll have to throw it away, right? So it could be a bit wasteful, but of course it depends what you do overall. So I just said that. So if we take the normal to be each of the basis vectors, we get the 3 components on the diagonal, but we want 6 components. So this will correspond to rotating it about the X, Y, and Z axes, which we usually put the sample rather than the whole laboratory. But we still need another 3, right? So we can just choose 3 other directions to rotate it around and change of variables. It gives you the off-diagonal terms. So yeah, you really need at least 6 axes to rotate it around. If you're going to do it, rotate it by axes. You don't need to do it that way, of course. It's just easy to see how to invert it. What you do is just measure as many directions of lines as you can in the time, you know, fairly well spread out in the space of directions of lines. Oh, that's just how to get the off-diagonal terms. I guess that's fairly obvious that you can. So that's a little introduction to the theory of racing. And I want to say this is billed as part 2. If I don't get through all of it, then you know that will reappear in part 2. Okay, so diffraction tomography generally it's kind of blend between X-ray diffraction type of things, crystallography, right? It's very old. You get a crystal that's meant to be homogeneous spatially, even if it's anisotropic. And then you fire an X-ray at it, you look at the diffraction pattern, looks at lots of diffraction patterns, and assuming it's a crystal, you basically inverse Fourier transform. You don't know the phase, but you kind of guess the phase, and then you get a nice picture of a typical crystal unit, right? So, you don't like very much. Unit cell. And so on the other hand, tomography, you can typically ignore diffraction and just see what gets through. So diffraction tomography is some kind of blend of the two of them. For each ray, you measure a diffraction pattern. So in a way, the idea is it is taking account crystalline structure on some scale, but it's spatially variant. So there's definitely you have to be careful with the different scales. Kind of two-scale problem where on the width of the beam is sort of quite wide compared to the dimension of the unit cell, right? So from its point of view, the crystal looks almost infinite, and so you can treat it in the same way as you do crystallography. But in the large, the beam goes through lots of different bits of crystal, and so you get the sum of the diffraction patterns instead of just some spots. If you've got lots of crystals, you get something that blurs together into a pattern. Okay. So here's an idea of how to formulate it. I think a rigorous mathematical treatment would start with a two-scale approximation with some estimates about how small the length scale has to be compared to various other parameters. So instead of a scalar, what we do, or a tensor, we do something like this. We have a vector Q that they think of as reciprocal space. I mean, in other words, it's spatial frequency vector. Reciprocal space vector. So the length of this vector is the spatial frequency that it's talking about, and it's also got a direction. And the idea is that this sort of unit of scattering, which is about the width of a beam, can be described by what we might think of a scattering cross section. In other words, when the beam comes in this direction, then in the Fourier transform variable, what happens is this diffraction pattern. Oh, let me say, because the diffraction pattern is captured on the screen, which is two-dimensional. But if you captured all the pictures on the screen, it would be a function of the sphere, right? So we're thinking that each point has a function of the sphere, or the reciprocal space in that. But of course, we only get for at least some problems the component the plane of the screen. So we'll think of the direction vector xi as being perpendicular to our screen. And so we only know this for Q's that are perpendicular to xi. Right? So that's, otherwise it would be much simpler. So we call this a generalized ray transform because it's a function now, not specifically, not just a tensor, but a whole function on a sphere. And we're just thinking about the dimension counting is a very useful guideline as kind of a rule of thumb. And the space of lines in 3 dimensions, as we've seen, is 4 dimensions, right? Whichever way you cut it, you need 4 things to describe it. In scalar tomography, we're only looking for one function of 3 variables, right? So if we measured all the possible data, we'd have a function of 4 variables, which is great because it's overdetermined formally, which allows us to check if the data fits the model. In practice, typically one collects some 3-dimensional subspace manifold, I guess, of directions, which could be helical, cone beam tomography, or various other geometries. But in any case, it will depend on 3 parameters typically. So the 4D data we think of as complete data, whereas the sets of people practically use the kind of That's actually incomplete. You try and make complete data, but not all the data you put there. And of course, the effect of that truth, it might have a unique solution, but it will affect the stability of the reconstruction as well. So if we have, say, a six-dimensional unknown image, so for each ray, that's 4 dimensions, we've got a screen, that's 2. So we're measuring a function of 6 variables. Okay? The parameterization of the line and the parameterization of the screen, 6. Okay? Now, the thing we're after, we've got 3 spatial variables, and we've got a point in space, and for each point in space, we've got a function on the sphere. So it's a function of 5 variables. So that should be all right. I mean, it might not be, but at least, you know, at least it's possible. So it turns out it does have a unique solution. And actually, it's because exactly the same trick that Charles used for the tensor version of this works here. So of that sphere, we just take the value of the pole, north pole of the sphere, so this is the plane being the equator, and each plane, that's invariant. And so, you know, rather wastefully, we have whole diffraction pattern. But the point of reconstructing this space, we're only going to take actually the values on line, because for each absolute value of Q, spatial frequency, that's a circle from the diffraction pattern, something happening on a particular length scale. And then we only take the value at the top of that circle to reconstruct the reciprocal space function for that length scale as the value of Q. And we reconstruct the scalar. So again, could be a bit wasteful because, you know, we threw away most of the data. But that means it has got a unique solution, and so you happily then go and do it numerically. Because this kind of is related to the tensor version, because if you wrote the reciprocal space function as a polynomial in Q, then the components of that polynomial can be a tensor. So, you know. So one particular type of diffraction tomography, because we could use variously X-ray, neutrons, or electrons. Anything I'm missing? That's pretty much what people do. I don't know if anyone's tried this view on this. And in a way, you can do it with lower frequency electromagnetic waves. And, you know, for example, in radar, you think of a scattering cross-section, thinking of finding anisotropy objects. So there are other cases where there's similar kind of mathematical thinking. Anyway, SAXS, small angle X-ray scattering, really involves the fact that the deflection of the X-ray beam is small, which means that the length scales you're looking on are quite large, right? Because it's reciprocal space. So, okay, so you're looking for things that are larger than the scale of crystals, right? And also, if you see one of these things like stars and light source, very, very long beam, again to collimate it parallel, and you can put the screen a long way away from the sample as well. So, you know, you can make that suit your camera or way for the camera to measure it. But the deflection angle is small, and it means you can. You can take a feature called sine theta approximation. Anyway, so they actually do this, and I get a sample that's not crystalline, but it has some kind of spatial orientation on the relevant length scale that you're measuring. And yeah, so I said before, you measure the diffraction pattern, you can rotate it this way and this way, this way, this way, and that. And then for each of those, measure.
Okay.
Yeah.
I mean, for the inversion in this case, is it done by the method that you described?
So the only people who tried it do it that way. In other words, they get some software for, I understand it, plane by plane, ground transform.
And you could say for each correct exactly what.
Yeah, right. But it's not exactly that because they haven't necessarily sampled it in exactly that order. So
Like 3 minutes.
yeah. And in any case, we'll have somebody from this group.
Oh, yeah. Depending on the kind of size focus, beam at the point of focus, I guess you get to kind of choose how you trade between resolution in the K-space domain and in the signal real space model. Yeah. Just wondering whether you can, say you have something like synthetic aperture radar, could you do a thing whereby you could maybe trade some spatial resolution to get a kind of look at some kind of microstructure, locally, and do a similar kind of thing?
Sure.
Yeah.
And I think it's all about those trade-offs. And I think the thing that we're sort of lacking in this is a rigorous asymptotic argument for what various things have to be small or large to what order. And I think when physicists do this, they almost, without thinking, set it up so it's in a sweet spot where it's going to work, because they kind of know what kind of deflections they expect, and they don't necessarily write down a rigorous mathematical, but they'll do a back of the envelope calculation and they'll operate in that sweet spot. And I think that's the same in radar. Yeah. I mean, I think the question for us now is, if we do make it rigorous, then we can say how far they could push that approximation before they need to use some different model. Right? So that's quite a useful thing. Yeah, so Marianne Liebler, we've done this sort of thing, and they have got reconstructions. And what we're seeing here is the scattering vector in per nanometers. And I think the thing to look for is that there is something going on at this particular scale, right? So at each of these length scales, we'll get a functional sphere. And on some length scales, it might be isotropic, right? So it would just be uniform, constant functional sphere, right? In some length scales, it might have a preferred direction. So it might look like a quadratic function on the sphere, right? And you diagonalize that like an ellipse, and you have eigenvectors, and they're preferred directions of something lining up. There might be some kind of strange mixture of preferred directions. Maybe there's two things that are oriented differently, or there might be, fibers and sheets and so on. And so you might get something that's not a quadratic function. And then you have to work out how to analyze that, but that would be problem specific. And it's kind of quite an interesting question I haven't really addressed. I mean, at least partly, the question is it accurate enough to actually fit anything more than the best fitting quadratic? It is a bit, but you get diminishing returns if you go to high order polynomials. So I think you'd have to have a case for using it before you put effort into it. I had some slides here just that my colleague Alexander Kozanski provided, which just showed you things happening on different length scales. In this case, in a tooth. And the only take-home I want you to look at is there's definitely different orientations at different length scales. That's the sort of thing we're after, reconstructing different lengths. There's also a thing called WAX, wide-angle X-ray scattering. And of course, it's wide-angle, it means looking at smaller things. Right? It's also slightly more complicated because it's not, the angle is bigger, so sine theta isn't necessarily close to theta. And so rather than being like a longitudinal, but like a transverse ray transform, it's a bit of a mixture between longitudinal and transverse. I mean, it's kind of think of it as being something like it's a bit of this component and this component. So it's a little bit more complicated, but in in this case, obviously, on first stab, it looks like it's circularly symmetric, but if you look closer, it's thicker and thinner at some length scales. So there's something going on at those different length scales. And the length scale is quite distinct. Presumably, it's because of the dental enamel has crystals in its crystal structure. I guess maybe it's quite obvious that if you have a function on the sphere, and I'm thinking of absolute value of Q constant, you can expand it in cell harmonics. Expanding the cell harmonics is exactly the same as polynomials in the sphere, actually. But it is just that from that way, but for each fixed length scale absolute value of Q, the coefficients of a symmetric rank whatever tensor if you go up to cell harmonics of a certain order. So it falls back into the familiar ground of symmetric tensor fields. And I think from a mathematician's point of view, the thing that might be exciting is that we have lots of examples of rank 2 tensors. I mean, strain, a lot of anisotropic material properties of rank 2 tensors. You maybe have seen a rank 4 tensor once, and it was the elastic modulus tensor in linear elasticity. But there's not a lot of higher rank tensors around. But if you start representing a function on the sphere, it's however many terms you need to approximate that, right? So it comes in naturally. And in fact, a lot of these anisotropic properties that are represented by rank 2 tensors and are representing the fact that the material has some kind of orientation, that's actually a truncated Spark harmonic expansion, and maybe the other components are too small to measure, but it often comes down to. Okay, so I guess that's all. Yeah, well, so if it's a Spark harmonic expansion, it is this case where for that fixed, I've said big Q, then it's a tensor. But for each of those length scales, for each of the circles on the diffraction pattern, you get to do the transverse ray transform of a tensor field. And the order of the polynomial might be different at different length scales, because as we saw on the T thing, some length scales it might be isotropic, some length scales it might be much more complicated. So you'd have to look to see. You'll probably do it at ranges of length scales that have the insystem structure. Yeah, and you do have to process a bit to get the TRT data from the diffraction pattern, but okay, so you probably don't use explicit inversion models. So actually, mathematicians love explicit inversion models. Right? So everybody was delighted when I done the Katsovich, for example, had an exact reconstruction formula for helical scale cone beam, especially given that most X-ray scans in the world are hospitals that do helical scan cone beam. Right? That's what, in a way, really matters. The volume. And it's a weird geometry, but there's a nice. It's horrendously complicated that only a mathematician would thought of, but we love it. Formulas to invert that explicitly. It's really interesting why it's not used, and it's almost like one of these fairy tales. We have to be careful what you wish for, because this inversion formula uses correctly determined data, more or less. It doesn't use really much of the redundancy in the data. And therefore, it makes a very plausible picture that's wrong if you have certain errors. And the sort of errors they have are geometric errors, like just the center of rotation in the wrong position, or something geometric or something not calibrated. And because it's sort of formally correctly determined, it gives you a really plausible image that give it to a doctor, and they'll give Latin names to the artifacts. So the people who make X-ray machines are wise enough to say, we're not having that. That will be terrible. What we want is when the data's wrong, it makes a blurry picture, and the user thinks, oh, it's blurry, right? And even if you use an approximate reconstruction algorithm that are commonly used, but you do it on overdetermined data, they kind of average it over inconsistent data and makes a blurry image. And in fact, the first thing that was done alongside to fix it is to make a blurry image and use the blurriness of it as a fitting parameter to fix up your geometry. I mean, obviously, the best way to do it is that, but it's a neat idea. Then use the elegant explicitly. So explicit inversion algorithms with integral operators are not, are very exciting from a mathematical point of view, but they're typically hard to incorporate systematic a priori information, because usually the regularization happens on the data side, which is kind of morally wrong, right? Because a priori information should be about the image and should be neutral about how you measured it. But they serve a very useful purpose at the very least to inform us about what sort of things will happen when we just write the whole thing down as a massive matrix and try and solve it with some regularization, right? Explicit uniqueness and stability results of subsets of data are really important, even if they're not really what you want to do. I mean, typically they do work well for relatively stable in response and a mildly opposed one. But as soon as you get severely opposed, then you need to put in some prior data to get a stable solution, and then you can't do it. Okay. So there are explicit reconstruction algorithms that are of the filtered back projection type for the transverse ray transform. I don't think anyone's used them. They've used a simple trick, and what Sean said, rebinning, right? You can get the data exactly that you wanted for that, but you bin them into planes that reconstruct. Okay, so I'll go into neutrons, and I wonder how far I'll get. Again, if it's a quick summary overview, and maybe that's all right, because not only am I going to talk about these things more, but we're going to have some of the real experts on some of these techniques come in. So, polarized neutrons. I mentioned already, neutrons have a spin, I think like a little spinning top rather than just a ball, and this spin, like an axis, processes when it's in a magnetic field. So it moves depending on the orientation of the magnetic field. And actually, the neutron only cares how long it's put in the magnetic field. It's kind of independent of its motion. Just how long it spends in what magnetic field determines how much its axis starts to move with the magnetic field, right? So that really makes a neat simplification compared with something like Maxwell's equations, where the direction is very much part of the interaction. Yeah, so the faster the neutrons, the less time they spend in a magnetic field, so they don't change that much. And fortunately, our neutron source is like a race, as I mentioned. You have a burst of neutrons at a range of energies, and the fast ones get there first in a race. So they're kind of sorted in energy. And you can choose a band of time, and that's more a band of energy. And okay, so the point is, this is really for measuring magnetic fields or magnetic materials. Materials have a magnetic property, and the idea is to make a 3D image of a magnetic field without poking things in. I mean, on the neutrons, right? The neutrons pretty much go through most things pretty much not particularly interrupted. I mean, that's a benefit of neutrons. But a polarization change with a magnetic field. Yes, polarized neutrons forming. Right. So actually, I'll show you a picture. Using various magnetic devices, you can make a polarizer and an analyzer in the same way you can do for optics and polarizers. So, yeah, you put it through something that lines them up so they're all polarized in more or less one direction, or at least a distribution about one direction. It goes to the opposite, changes, and then you put it through another polarizer, and then you rotate them around instead. You measure the polarization, which is the same as you do with light. It's just that the polarization vector is in 3 dimensions. or on a sphere, let's say. Okay, so here's the governing equation, basically. They call the polarization things of a vector sigma. It's not exactly a vector, it's just direction. But if B is the magnetic field, spatially dependent, and then you go along a line, our typical x plus s line. The point is it satisfies an ordinary differential equation. Now, you might know that for X-ray tomography, that has a differential equation to it. So it's a transport equation called Lambert Law. And this is really common for a lot of tomography techniques because what happens is the amount that gets through the next bit of the ray, you have something coming into a voxel, and something happens, then some of it comes out, right? So it's naturally formulated as a differential equation of the rate of stuff disappearing as it goes on voxels, and hence a transport equation. And in this case, sigma is a vector, and what happens is you get the vector cross product with the magnetic field. So it's not trying to line up. But B is a function, so it's a system of linear differential equations, right, in T, along the line, in S along the line, right? And so imagine what happens is you've got your neutron spinning, minding itself. There's goes to something no magnetic field, and then as it goes to the magnetic field, changes. But it's just saying the rate of change is proportional to the vector product of the magnetic field and the spin direction. And that's linear, right? It's linear in sigma. So it's a linear system of all the differential equations. Now, that's not too bad, but in the scalar problem, the Lambert law, it's just a scalar version of a linear first order differential equation. So you can just solve it with an exponential, and all you need to do is then take the log of your data, and the operator is linear. But you can't quite do that even with a simple variable curvature equation. And the thing that we're measuring then is the relationship between the input and the output polarization. So geometrically, we organize the polarization to be in some direction when it comes in, and then we measure it when it comes out. And then we change the input and measure with the direction of the output. So what we've got is a kind of initial to final map for this differential equation, right? Put in initial data, measure the final state. Yeah? But that's nonlinear because we can't do the log trick, the matrices, largely because B and its derivatives along the line don't commute typically as well. The matrices associated with vector cross product with B doesn't commute with this derivative. So that's why it's called a non-Nonbillion ray transform. It just means it's just the matrix is not commutative. So there's a whole theory of non-Nonbillion ray transforms, and it wasn't really clear when Eskin did this what his motivation was, but there was some problems. There was some other more abstract theoretical problems that motivated, and it turns out it is what we need. So what Eskin said was you've got a function of x and xi, in other words, of lines, right? And you've got this transport equation, in other words, the directional derivative and the direction you're going is something multiplied by u. Okay, so u is a vector. And while the space is two-dimensional, the vector could be any dimensional, right? And in our case, we're thinking of a plane at a time, and our state is the polarization. But you know, it works for any dimension of u. And we take the directional derivative of it, and all we need is that it's a spatially dependent matrix. One part, you know, it's just doesn't depend on the direction, right? And the other bit is linear in the direction. So this is more than we need, because I pointed out the neutrons actually don't care what direction they're going in, just how long they spend in the magnetic field. right? So in this formulation, for our problem, the A1 and A2 were irrelevant, like some other physical problems where they come in. But in fact, we only want the A0. But I mean, kind of interestingly, for this problem, he proves uniqueness of solution, but it's kind of up to what he thinks of as a gauge condition. So AI dash and A0 dash give you the same data as the test about by this matrix values function G. It turns out, though, that it's very easy to see that if you know A1 and A2 are 0, then G has to be identity as well. So nicely, there isn't a gauge condition for our problem, and so there is a unique solution. This proof uses complex analysis. It's quite hard to get hold of what's really underlying it, and in particular, it's not constructive. We can't, or at least we don't know how to make it constructive. So it tells us a unique solution without telling us what it is. Well, okay, it just gives us a license to go and do it numerically, right? With at least some hope that the more accurately we measure, at least eventually. In practice, it's nonlinear. We're going to use some optimization. We might fall into local minima. It's telling us that at least as everything gets more accurate, there's a global solution. So this is an interesting example of a nonlinear inverse problem. It's rich because we're measuring a matrix for each line, and we're trying to recover a vector field, a magnetic field. Right? It's nonlinear because we have an OD along the way that's not scalar, and that's kind of typical of, you know. So it's nonlinear. It's not like, you know, microwave imaging or electrical beam tomography or diffuse optical tomography, where everything affects everything else. The point is, it's only the things along the line that affect the measurement, but it's nonlinear on that line. So it's kind of local, but nonlinear. So it should be easier than the things that are, everything's coupled to everything else. Nonlinear property. In particular, the linearization of our problem, you know, it is some linear problem that we can actually reduce to scalar random transforms by looking carefully at which components we're doing. So, and that's been done actually. So, the point is though that the linearization assumes that the either the magnetic field is really weak, or the neutrons are going so fast that they, the strong magnetic field, but they're going so fast they don't spend much time with it. And that's all very well. And you could say, just for the sake of having these linear problems, let's get hugely energetic neutrons and only use the fast, right? Instead of using the thermomagnetic. But as it stands, you get a whole range of energies, stroke speeds, for free. And if you only use the really fast ones, you get an inaccurate reconstruction, right? You get it'd be like a low count X-ray or something like that, right? So you only get counts of individual neutrons. And remember also, you've got to rotate the polarization directions for every projection as well. So each of those elements of the matrix would be inaccurate if you only use really fast ones. But there is a natural thing to do, which is use the really fast ones to get a rough solution to the nonlinear problem, and then use that as the starting point for a nonlinear fitting algorithm. So it's kind of sweet in that way because you get all the energies for free, and it just, the more you use, the slower the ones you use, the more nonlinear it is. And especially if you want to cover a range of magnetic fields where it's less strong in some places. I kind of said all that, skipping through it, and I just want to say a little bit about strain, because we have our Bragg edge expert. So yeah, I hope we'll have more talks on this, but let me just set the scene. You have parallel beam of neutrons as before, but the sample we're looking at is polycrystalline. So, for example, a metal with fine crystals, or possibly a powder, it's got lots and lots of RNT crystals. Okay? They're oriented randomly, so the orientation is uniformly distributed in directions. Of course, it's not so true in metals because usually a whole point of metallurgy is to align the crystals in some direction. But you know, there's like a really annealed piece of metal. And what we assume is, for the width of the beam, we have a notional kind of voxel size, about the size of the beam. And over that beam, we've got every direction of crystal. So a random on that scale. It's hard to actually get that. There's a sweet spot. It's also saying, you know, you use a bigger beam, there's kind of a lower spatial resolution, but you've got a bigger sample of random directions for the crystals. Right? So that's the sweet spot. And what you get for such an experiment, for one ray, you get a time of flight graph of the number of neutrons you measure, and it's put in wavelengths, because wavelengths relate to frequency and energy, and therefore ultimately length scale. So what happens is that the crystals have certain crystallographic planes, and then neutrons are Bragg scattered just as though they were waves. But there comes a point where you're doing the sine inverse of something that's bigger than 1, and then suddenly there are no neutrons scattered in that direction. So you change direction. So what you see is suddenly a drop off in the number of neutrons because it's gone over that Bragg position. And because we've got crystals in all directions, there'll be some in that, there'll be quite a lot in any direction, including ones which are lined up to that Bragg angle. So what happens is you get jumps in the spectrum that correspond to the distance between the crystallographic planes. Okay? In that image. Well, first of all, we don't measure the scatter ones. Right? They just go off somewhere else. We only measure the ones that don't get scattered. So you can do that. You put detectors all around it, but that's a good point. In contrast to the X-ray thing I was talking about, and you can do small angle neutron scattering. We're just, we just measure the ones that go through. So we don't care about the energies of the scattered ones. But,
the ones that don't affect that are scattered ones.
oh yeah, sure. Yeah, right. Yeah, so it depends on the material. Some materials are better. So, all things being equal, you get a nice, clear, distinct jump for one of the sort of more important crystallographic directions. And that tells you what the separation between those crystallographic planes are. Now, we get our sample and we apply some strain to it. And each crystal gets strained. And each little crystal is now a strain gauge, because when you squish it, that distance between the crystallographic planes changes depending on the component of the strain normal to that plane, right? So yeah, if it was unstrained or had a uniform strain, we just see a nice sharp edge. The interesting thing, and I'm just going to summarize it very quickly, is that the beam goes through lots of voxels. Voxels have lots of crystals, but the strain varies by voxel. So even a fairly smooth strain that's roughly constant over a voxel but changes as we go on the beam, then you can think of that as each of those has a different separation between the crystallographic planes. So each of them makes its own Bragg edge. And the more volume of strain in that direction of that magnitude, the bigger the jump. So it will broaden this out. Time for the cartoon. Yeah, so if you think each Bragg edge was something like this, and then we add lots of them, then you know, this is a Bragg edge that's on several different Bragg edges, but of course it's continuum, so it blurs it out. Right? If you subtract the linear part, it would actually be steps, and you know what that is? It's a cumulative histogram. Right? So Q, if you ignore the slope bit, so take it away, and like say you differentiate it, it simply is a histogram that tells you what the distribution of strains are along that lane. If you take the first moment of that, it's the mean, and it turns out that that mean is simply proportional to the longitudinal rate transform of the strain. And it's the longitudinal rate transform, so it's got a null space. And the null space are the things that are called potential, that are symmetric derivative of vector field. Oh, wait a minute, what's strain again? It's a symmetric derivative of a vector field. It's like exactly the thing we wanted, exactly the thing in the null space. And people actually tried to do this and published it, and interestingly got something, you know, but well, it's in the null space. It turns out, though, that when I say that's the null space, it kind of means on a continuum thing on the whole of space. And what happens with elastic solid is it's got a displacement vector inside the object, and outside there's nothing happening, so call it zero, so like strain zero, and then it's got a boundary. So it's really the boundary conditions where it's not a gradient or something. So in a way, what you think you find is the boundary condition. So the other thing you could do is say, well, we don't just have the first moment of this distribution, we have a whole histogram, right? So what can we do with that? And the question is, can we extract, that's just a symmetric thing, I wave my hands at. And Kyle, would you like to introduce yourself?
Hi, I was here for Bill 2 years ago now, when I was back in Manchester on the Bragg edge problem. I'm now here in Cambridge.
Okay, so yeah, this is work we actually did experimentally at the ISIS neutron source, and we have this sample which is a ring and plug. So it's a slightly eccentric plug that they cooled down or heated up the ring, popped it in, let it equilibrize in temperature, so it's got some strain locked in it, right? And we know the strain; it's very well characterized, and we also had an unstrained sample. Chip in if I get anything wrong. If you remember, it's 2 years ago. So we did the unstrained one and the strained one, and we see a difference. But the real question is, can we get the second moment? Because we can definitely get the first moment. And of course, because it's very well characterized, along one line in the detector plane, we know what the strain should be, and it should be rotation. Oh, no, so one component of it. Rotation.
Yeah, and it's sort of fine.
Yeah, yeah, we should be uniform. Yeah. But the point is, we have analytic solution for the strain because it's that simple. And well, it looked to us like our fitting of the second moment does look quite close to the predicted line. And I used to say, good, that's the caption from the figure in our paper. And say enough to say that it was an inverse problem on its own, just to recover the second moment from noisy data. But it looks like one that we can get the data. So you either do that, and then you have to do something with a second moment, or the other thing. And I won't say much about this because Chris Wensrich, who's the author, one of the authors of all these papers, is probably coming next week. So perhaps we can extract a seminar from him. His point is to assume the elastic equations have inside the body and to add those constraints even though it goes in.
The question maybe is Well, I guess there's two questions. First, can you be precise about what exactly mean by the second moment? And second, is there a like mathematical model like similar to the your Lambert Law that one we had in that describes the curve?
There's a bunch of assumptions going on here. And I mean, in particular, the neutrons do get attenuated a bit as they go through the material. So, you know, ideally you calibrate that. And there's this two-length scale approximation. And you're assuming that something does, the neutron doesn't get scattered again and happen to end up going straight to your detector, right? So there are quite a lot of physical assumptions that you have to operate in the sweet spot of, which possibly affects how useful this will be in the end. And I guess our approach, and perhaps Chris Switch's as well, is to see if we can do it in an ideal situation first. Right? See if the measurements make any sense in an ideal situation. And you know, they fit the model, but there's a distribution of errors, and maybe that's the thing we don't really know. I mean, it's inverse problem people, we ask that question: what's the distribution of errors in your measurement? And even getting understanding the properties of the beam, you know, the distribution of energies, the non-uniformity across the beam, and so on, is something that there's quite a lot of work, and people work on it, but you know,
I mean, so what you're saying that there's so many different factors that you don't know an exact model.
Well, it's stochastic anyway, because it's just like an alignment. So there's a part of it that's going to be stochastic. And what happens is, if you just wait longer, you get more neutrons. And eventually it becomes a normal distribution, right? But if you don't have all week, you know, to measure each projection, then it's going to, one, it's going to look more like a proximate distribution, and also it will look like a kind of sparsely sampled draw from a proximate distribution. And so, yeah, ideally you take out of that distribution. So even when you calibrate and respond to everything else, you only got so long that you put on beam time. So you have to plan your measurement so that how long you can do these projections.
I believe you are looking for error, but I mean, I guess what I'm looking for, what's that for the question is, like, you have those curves that were like the strange curve and the strange curve. Like, where do those come from?
Oh, the curves come from an analytic bridge. It's such a simple object, you know, it's well characterized, but we need one. Yeah, so we had a ground truth.
Yeah, but then that's like, how do you get from that to the Bragg curve?
Right, okay, there's actually either not know or they keep it secret and don't tell me. So it's only, I mean, going from a simulation of the material, like the distribution of nuclei, to a Bragg, you know, a Bragg edge or even a scattering thing, it's not something that they can just do purely with physical models. Is that right?
Yeah, so we do have like a physical model that we're using that Bragg edge draw out, but it was in the literature from like 2001 sort of thing. We re-derived it in the case of it based on logarithms. So
it's still a bit handwork.
yeah, there's a Gaussian that we use as an error term.
Yeah, right. So there's some kind of exponentials that have physical reason for, and there's some Gaussians that we don't really know they're Gaussian, but it's a bonus there. And so there's a lot of empirical fitting just to do a basic experiment that you get from science. Yeah, can't look very carefully at the model, but you know, it's not all physics coming to it.
Yeah.
Yeah, right. Yeah, maybe So Carl works on something else. I couldn't manage it yet. He's in Cambridge, so perhaps he'll around it. Because it, wasn't ever a problem. I'll put the slide on the link to this talk. I suppose there might be a question in Zoom, but I don't even know if there's anyone on it. Oh, the screen sharing stopped. Oh, yes, that's all right. Nothing in chat. Okay. Yeah. Anyway, I think I'll sort of leave it at time, but I'll be around for this.